we're very happy to have Raman today, who will tell us about this twisted representation of quantum toroidal.
Thank you very much. Thank you for invitation, for opportunity to give a talk. Actually, I have to apologize because me and Misha already gave a talk on this subject after this lockdown and Zoom seminar started. But I have edited a bit my presentation for this.
I don't think everybody from the audience attended your first talk. So
I also hope that but I think that there are some people who attended like Misha's talk, but okay, so like I don't want to to over advertise myself, but okay, so let us start. So the plan of my talk is the following. I'm starting from the motivation. The motivation is Gorsky-Negut's conjecture on K-theoretic stable envelopes. Then I will explain my construction in. So my construction is about is a construction of a representation of quantum toroidal algebra. This algebra depends on two parameters, Q1, Q2. And I'm going to consider a very special case where Q1, Q2 equals to 1. This is in McDonald notation Q equals T. This is a very simple case where McDonald polynomials are becoming just Schur polynomials. The problem is solved due to very classical semi-infinite construction in this case. And I'm gonna briefly recall it for you, and then I will explain general case where this constraint Q1, Q2 equals 1. No, where we put away this constraint, and our approach to the general case is like the deformation, a deformation of the example. So I'm going to explain what is deformed, what is not deformed, stuff like this. Okay, Gorsky-Negut's conjecture is about K-theoretic stable envelopes. We will consider the following setups. So our variety X is like Hilbert scheme of J points on C2. We've got a torus section, which is induced just C cross times C cross. And the action on Hilbert scheme is just induced from the action on C2. And also these K-theoretic stable envelopes depend on some real line bundles, some slope parameter, whatever you call it. And so it's just multiple of O1 on the Hilbert scheme. And this multiple alpha is in real numbers with some walls excluded. These walls are basically like rational numbers with denominator which does not exceed j, where j is the number of points. Also, I want to consider not just like actually, the stable envelopes depend not on alpha, but like on a chamber between two neighbor walls. So it makes sense to say, okay, we are on a wall. The wall is called M. It's a rational number. And we can move slightly to the left or to the right. And this is like, I denote this alpha equals M plus or minus epsilon, and epsilon is not really a number, but just an infinitesimal shift. Okay, and the conjecture states that, okay, let this wall M be n prime over n. Assume for simplicity that greatest common divisor of n and n prime equals 1. Then the conjecture states that there's an action of quantum affine algebra, GLN hat quantum affine group, on K-theory of direct sum of Hilbert scheme for all j's from 0 to infinity. Such no, so I said that this action exists, and there are like two properties. First, that this representation is level 1 integrable representation, and the second property is that stable the change of basis, like transition matrix from one basis to another basis, from this m minus epsilon to m plus epsilon, is the same as the transition matrix from standard to standard base. Okay, maybe I'm saying this in the wrong way. So I mean, after this identification of this K with integrable level 1 representation, okay, maybe, so, sorry, let me say it properly. So there's a notion of standard and co-standard bases in level 1 integrable representation. And I'm not really expecting you to know what are standard and co-standard bases in integrable level 1 representation of quantum group. This is something from theory of quantum affine algebras, and I'm going really to explain this during this talk. But okay, the conjecture states that we like have an identification, and with respect to this identification, this stable bases go to the standard and constandard basis. Okay, sorry, I did this a bit messy. Maybe there are like some questions so far. Okay, no questions. This means that maybe everybody knows, so hope not lost. Okay. So like when I'm starting to talk about this conjecture with Andrei Okunkov, he says, okay, but this conjecture was proven before it was stated. And actually, it's not the subject of my talk, but I want to use the opportunity that this is like informal seminar, and also like Andrei encouraged me to put this slide in my presentation. So I want to like discuss what
this is Andrei. Which Andrei? Negut or
no, you said
did
that
I?
Yes, when I was
you
talking...
certainly can discuss it. Not I haven't seen
Yeah.
this particular slide, but I'm all for discussion of this.
Yeah. So am I actually like there are like two claims, and I think that these two claims are not in the literature yet. So the first claim will be in paper of Okunkov and Bezrukavnikov, which is like the most famous unpublished paper, I guess. And this states that K-theory of rational Choroidnik algebra category O of rational Choroidnik algebra coincides with K-theory of Hilbert scheme. And here are some details. So rational Choroidnik has some central element. We assume that it equals to m, and this is the same as m as on the last slide. And after this identification, this stable envelopes goes to Fermat module. And Andrei, do I understand correctly that another stable envelope like m plus epsilon goes to like costandard objects, right?
Yeah.
Okay, great. So this will be in this paper.
So in general, if you have stable envelopes, then if you take the dual of a stable envelopes, it is also stable envelopes for different parameters.
But actually,
yeah.
maybe I'm not
anyway,
sure.
the dual of a stable envelope is something else, and so I mean it's another object of the same kind. So so if you have some statement for stable envelopes with one parameter, then there's also statement for stable envelopes with some dual set of parameters.
Okay, great. And the second claim, which I discussed a bit with Vanya Lossev, and he said that there are like some technical difficulties, I guess, but maybe I did not understand all the things which Vanya Lossev said, so maybe I get it wrong. So if there's something wrong, this is not Vanya Lossev's fault, but this is entirely my fault. And like you shouldn't ask the questions, but this claim is that there's like categorical action of this quantum affine group on category O, such that category O is again K-theory of category O is integrable level 1 representation, and these Verma and co-Verma modules, the classes correspond to standard and co-standard bases. Bases. So like this is a long way, maybe not too long, but a way through category O of Cherednik algebra. And so this is why Andrei says that this conjecture was actually proven before it was stated. Actually, I'm going today to discuss something. Maybe the conjecture will be proven anyway, and the conjecture will be proven many times. I hope so, but I'm using like really a different approach. Yes.
So you shouldn't be apologetic about it. First of all, I said it may have been proven before it was stated. That was that's exact quote. And second, you should. I mean, you have a different proof. I'd say it's great, and especially since.
Yeah, but actually, I also don't have a proof yet. But okay, let me try to explain what is all this about and what am I personally doing. Okay, so let me start with recalling some very basic stuff, and I hope it will be like very clear to anybody. So if it's not, please ask a question. And if you're sure, somebody is sure that I have to like move on and this is too clear, then also say it. Okay, so this is about semi-infinite construction. Let V be some countably dimensional space with basis Vj, and we consider algebra A bar, which is like Lie algebra of matrices with matrix coefficients Aij, such that these coefficients vanish far away from the diagonal. This Lie algebra certainly acts on this space V, and let us consider the following space. So it's semi-infinite power of V with some, like, let me call it charge R. What is this semi-infinite power? It has a basis of semi-infinite wedges. So it's like Vg0, Vj1, etc. These J's are just a sequence of increasing integers. And we have constrained that for n, capital N large enough, this Jn equals capital N minus R. So R is a fixed constant, and this is our constraint for the vectors. Okay, Also, I would like to say that an element in this Lie algebra A bar is degree k if it all non-zero elements are exactly on k's diagonal. Okay, and I claim that there is a certain central extension of this algebra A bar, which is called A. And this we care about this central extension because it acts. Oh, sorry, this has to be R, not M. Sorry for this. So this central extension acts on semi-infinite power for any R, for any charge. And this central element actually acts by 1. And we can say exactly what is action of any element x of degree which is not equals to 0. So it's defined just by Leibniz rule. So when you're taking like a power of representation of Lie algebra, this is how you act on this power. And I'm saying that due to this infinite power, you cannot no longer do this for elements of degree 0, and this why. But you can do this for all other elements, and for degree 0, funny stuff happens, and certain central extensions appears, stuff like this. Okay. Let me explain another approach to this semi-infinite construction. And actually, I'm doing all this not because I'm going to like review Kat's book and not for the sake of completeness, but because I really do need all this stuff to explain properly what I'm doing. Oh, sorry. So another way to think about this semi-infinite construction is to introduce some fermions, which is another word for Clifford algebra. This algebra has generators psi I and psi j star, where I, j are integers. And these are standard relations for Clifford algebra. So this is anti-commutator, and psi I, psi j anti-commutator vanishes, the same for the stars. And psi I, psi j star equals like Kronecker delta. Okay, and this is like Clifford algebra, and the representation theory of Clifford algebra is very simple. There is only one module with this cyclic vector and this like highest weight condition for this vector. And actually what I'm saying that this representation is naturally identified with semi-infinite power, which is like direct sum of semi-infinite powers with all fixed charge R. And this isomorphism goes as follows. So this psi actually is just wedge with Vi, and psi j star is derivative over V minus J, or if you will, this is like a substitution of a vector to a differential form, whatever you call it. Okay, and this R, this highest weight vector, is actually this semi-infinite wedge where the vectors goes like R plus 1, R plus 2, etc. And if you want to see this algebra A, then this is just a matrix unit Eij of this algebra is just psi I, psi minus j star. And it's like matrix of rank 1 is basically tensor product of a vector and a covector. I hope it's clear. Okay, and I will need like another interpretation of this for the sake of deformation. Actually, I need another interpretation of these fermions to be like intertwiners for this Lie algebra A. So like we consider the operators psi and psi star, which are intertwiners from tensor product of two representations like v times semi-infinite power to semi-infinite power, and I claim that these intertwiners exist, defined uniquely up to scale by this intertwining property, and actually no, they're deeply connected. They're connected to this psi's from the last slide as follows. So if you apply psi to vi, vi is an element of basis of v times w, w is any element in this semi-infinite power, then it's just application of psi I. And this psi star applied to an element w is this stuff. So we are like removing vj from this word. And I hope that actually this I hope that you at least believe me that it's tautology, just tautology, that these intertwiners are indeed these wedge and derivatives. Okay, this was like a crash course on Kat's book. And if there are like any questions so far, please ask. Okay, so upshot of what I said, that the action of a bar on V leads to action of A on semi-infinite power. And this actually gives us a lot of interesting, we have a lot of interesting subalgebras of A. For example, we can consider like just commutative algebra acting on V, just like Laurent polynomials. And if the action of these Laurent polynomials actually leads to appearance of Heisenberg algebra. So this xk corresponds to hk element of Heisenberg, but now this central extension. Okay, and another very nice example is affine GLN. So if we consider like matrices with coefficients in Laurent series, in Laurent polynomials, whatever, they act on Cn tensor with Laurent polynomials, and we can identify this with V like by Euclidean division procedure. So ER tensor y to the k goes to V and k plus r. And actually, this is like just an Euclidean division, but actually after taking, so yes, I have to say that if you take semi-infinite power, then certain central extension of this Lie algebra appears, and it's called Kac-Moody Lie algebra GLN hat on level 1. And actually this construction, you can say it's just Euclidean division, but actually it's has some, in my opinion, it's not trivial when you are starting to explore it. And for example, this action of from Gorsky-Negut's conjecture comes in this way. Okay. So the last interesting subalgebra in this Lie algebra A is Lie algebra of Q difference operators. So we can start from associative algebra of Q difference operators, which is generated by X powered by plus minus 1, D plus in power plus minus 1 with this Q commuting relations. And this algebra definitely acts on Laurent polynomials. And if you, as we did, identify Laurent polynomials with our favorite space V and take this semi-infinite power, we obtained so-called Fock, no, I will call this Fock module F. Okay, so when you are acting on semi-infinite power, then there appear central extension. And I want to consider not one-dimensional central extension, but actually two-dimensional central extension. The reason is then otherwise I won't get action of SL to Z. So there's an action of SL to Z on this central extension, which acts on C2 like SL to Z have to act on two-dimensional space. That's why I need two central elements. And this algebra diff Q1 is actually very important because it is a specialization, Q1 equals Q2 specialization of quantum affine GL1. Quantum affine GL1 has like many names: quantum toroidal GL1, elliptic hole algebra, deformed W infinity plus 1 algebra, Dinky-Okhara-Mickey algebra, and so on. Maybe I will also have to say Cherednik in algebra GL infinity, I guess. Okay, on this seminar, I have to say, like, this is, if you didn't recognize this algebra yet, that this is the algebra which acts on K-theory of Hilbert scheme by correspondences. Okay, this Fock module is then naturally identified with the K-theory. Okay, and my favorite approach to this algebra is to study. Okay, I'm sorry if you like to draw this picture in different way, like transpose x and y axis. Hope it's will not be a source of confusion. So I draw here on this picture, I draw generators of this algebra. Like for each point on the plane AB in Z2, I have a generator PAB, which is dA x d to the power a x to the power b. Hope you remember this d and x from the last slide, and which is appropriately normalized. Yes, and this is the picture of generators of the algebra. So on this row, I've got very famous McDonald operators. On the zero column, I've got just Heisenberg algebra, and my favorite presentation of this algebra is actually like take Heisenberg algebra and take this first and negative first columns. And that's it, and call like write a generating series for like columns, like say that EZ is a sum of P1k, so all elements from first column with coefficient Z to power minus k. Yeah, and Z is just a formal parameter. So this is like your power series, like what is my favorite thing to do after I like define this my favorite green, red, and yellow generators is I like to write some fermionic formulas. So this 18 formula is a formula which is expressing like action of easy current via fermions. So let me start from the beginning of the slide. So I define like two currents, psi z and psi star z, which are, as you remember, generating series of these fermions. And I say that this semi-infinite construction can be just tautologically, like if you think about this matrix units, then it's just tautology to say that like express action of Heisenberg algebra, like product of no, like this bilinear formula psi z psi star z. Also, his some normal laundering sign. It's some technical, not me explain this. Okay, if you think about this, like if you want to write a formula for action of affine GLN, then this is also possible, but you have to have like not one fermion, but n fermions. Let me call them psi I, psi, no, and the duals like psi j star, and the formula of, okay, recall that GLN hat was Lie, like central extension of Lie algebra of matrices with coefficients in y. So we take just matrix unit, tensor this y to the k, let's call it like this, and take a generating series. Okay, and this is the formula. So all these formulas are actually read from the semi-infinite construction. It's something easy. Okay, and what is my twisted representation? So as I said, there's SL2Z action, and you can twist a representation by element in SL2Z. So what it means that you can you will obtain, and you have a representation n m, and you will obtain a new representation m sigma, twisted one. It is this representation as m sigma is actually like the same vector space with a new action. What is your new action? You just have to apply sigma to an element of algebra before you act, and then you act via old action. Another way to think about this twisted action is just as soon as I'm concerned about this EF, and Heisenberg, like green, red, and yellow. So my problem is to write a formula like this Fermionic formula for these sloped generators like green, red, and yellow. That's it. Okay, and so actually, because maybe it seems like a weird problem for you, but actually it will. What I'm. First, what I want to say, it's not a tautology because we're using like a different set of generators, and actually this will give some interesting results at the end of the day. Okay, so what is my approach to this twisted representation? Okay, I'm going to use this semi-infinite construction, and I'm going to twist this Fock, which is the same as semi-infinite power of V. And instead, I can like take semi-infinite power and then twist. And this is the same as twist V and twist this representation V and then take semi-infinite power. Okay, and actually studied the action on twisted V is an elementary problem. It's not, it's like not a tautology at all, but this is like a problem for first grade students in bachelor, I guess, something like this. Actually, just a bit of calculations. So we say we can define this. So the proposition is that there's an action of this algebra of q-difference operators on this space, like Laurent polynomials tensor Cn, and this action is given by these formulas. So these P are actually my favorite generators, like green, red, green, and yellow. So these are red, green, and yellow. And what is on the right hand side? Okay, this p bar actually means q difference operators which acts on y. So remember, I've got this q difference operators on x, and this is like the same but for y variable. Okay, and this small EAB are just matrix unit which correspond to action on Cn. That's it. And this is the formula for the action of this algebra of q difference operators. And the proposition says that these formulas, the obtained representation is isomorphic to twisted just representation on Laurent polynomials. Oh, I'm sorry, I did not write it on the slide. So there's like slope, slope of these lines, and assume that this slope is n prime over n. Okay, and so here is n, and here is n prime. So n is essential parameter. So your representation space depends on n. And n prime is not really so essential, but it appears in the formula. Okay. So the picture we get actually like we are a bit closer to Gorsky-Negut's conjecture, because like we've got this space, semi-infinite power of these Laurent polynomials tensor Cn, and on one hand we've got Gillen hat action on it, and on the other hand we have these q difference operators. And I claim that this action, and actually deformation of this action, is exactly the action from Gorsky-Negut's conjecture. Are there questions so far? Okay. So as I said, that there's like fermionic formulas which are straightforward. So if you just look on the structure of this formula, I hope you can convince yourself that it's not hard to obtain these fermionic formulas using this matrix unity business. And I claim that these formulas define a representation of algebra of q difference operators for you, and this representation is isomorphic to this twisted Fock module. Okay, and now we are going to consider a deformation, and what is our deformation? Okay, so now we do not have constraint q1, q2 equals to 1, and we will introduce new parameter q, which is q1, q2 to the power 1/2, and we consider quantum group Gillen hat with this q parameter. It's well known that this Lie algebra admits semi-infinite construction. You can just take, it has like evaluation representation, and you can just take semi-infinite power of the representation, but you have to use not just a symmetric group, like you're considering like exterior power, so you have to anti-symmetrize, and you should use not symmetric group but Hecke algebra, affine Hecke algebra. This y, this which I had before, they are actually now generators of Hecke algebra. They commute this with this permutations in non-trivial way, and this makes life much harder. But nevertheless, this semi-infinite construction still exists, and no, that's it. Okay. What's about this algebra of Q-difference operators? Well, it becomes this well-known quantum toroidal GL1 algebra. There's still action of SL2Z on the algebra, and there's still like a evaluation representation for this algebra, and you can take this quantum toroidal algebra and you can twist the representation. But we do not know how to take semi-infinite power of the space. So what we did here is no longer applicable, at least on our level. Like you know, the problem is that this algebra actually, like there's an action of SL2Z on the algebra, but it does not preserve coproduct. You like have SL2Z acts on coproducts, and this seems to be like a technical difficulty for us. Okay, but nevertheless, there's still Fock space. It can be defined. You can write some very explicit formulas for action of my favorite generators EZ, FZ, and Fock and Heisenberg. And so we still can ask the question, like, do we have like explicit construction for this twisted Fock module? Something as explicit as we had on this slide. Okay, and actually I want you to concentrate on the formulas, like you have some bilinear expression, and that's it. I'm going to like these formulas has some deformation. Here I wrote them in some different notation, but I tell you that this is just deformation of the formulas. So to construct the deformation, I need some deformed fermions. And what are my deformed fermions? So these fermions are called vertex operators for UQ GLN hat. Okay, consider F0, Fn-1. These are integrable level 1 representations of UQ GLN hat. They're quite singular. Let me like not go to too many details, but they're not isomorphic. Okay, and there are intertwiners from this Fi+1 to CNZ. This is my notation for evaluation representation of quantum affine algebra. Tensor Fi. This is another integrable level 1 representation. And the key feature of quantum group is that coproduct is no longer commutative. So you can put your evaluation representation on the left or on the right, and you will get like two different vertex operators, and they are called like left and right vertex operators. Also, you can consider vertex operators in the other direction. So all these operators are determined by the property that they are intertwiners. Okay, and our theorem under construction, so it's not really a theorem, and you can check our recent preprint to know what is like a current stage of development. But nevertheless, let me not go to technical details and say that this is a theorem. And the theorem states that there is a formula like this. So it's I hope you will not get loose with this notation. So I write like so what's going on? First of all, I'm applying this phi. So I'm moving from f to cn times f. Then I apply epsilon, and I'm applying epsilon to this cn. So I've got like extra tensor factor, and I apply epsilon to it. And then I apply psi star, and it actually, for some funny reason, this cn appears on the other side, but it's just, okay, you can think that here in the middle, I also applied like formal permutation of the factors, and maybe I really did. Okay, and then this I apply psi star, and at the end of the day, I'm still in the fi which I'm started from. Okay, so this is my formula. And so there's like a technical difficulty about f. So you have to use like a bit different updated operators, but the difference is about, so inside GLN you've got like SLN and GL1, and the difference, this tilde stands for some modification which this GL1 concerned. GL1 is not rigid object. You can act with this GL1 by like different characters on these representations, and for some annoying technical reason we have tilde here. So we have like, no, these are a bit different operators, but the difference is in this GL1, so it's not really essential. Okay, and so this is like my deformation on these fermionic formulas. And yes, is there a question? Okay.
Yeah, so I don't know if I can.
Yeah. Okay, Andrei, you're okay.
Yeah, so now I've unmuted myself. So so is it easy to see that there should be a twist if you want this so you want basically F to be adjoint to E, and so if you think of the something acts of correspondences by whatever the Hilbert scheme, that the adjoint correspondence is something you know, there will be like the canonical class come in, and you need this twist by that's typical. I mean, in similar formulas in other situations, you kind of see that you have to treat two things differently, because otherwise it will not be like the adjoint operator will not be the adjoint operator.
So you're saying that this tilde comes from canonical class, right?
Yeah, usually that's what happens. Yeah. So
thank you very much for your remark. But unfortunately, I don't really know yet geometric meaning of these operators, but I hope I will.
But it is true that one should be adjoint to the other, right? So that's
yeah.
That should be this. You should see right away that if you have one formula, then the other has to be modified like that.
Okay, thank you. Okay, and so let me go back to my one of my first slides. So I promised you to explain what is standard basis is, and now still we learned what is like semi-infinite constructions, and I gave you loosely explanation what is Q-deformed. So, but if you do believe in Q-deformed semi-infinite construction, then I can just say that these semi-infinite Q wedges are this standard basis. Okay, and Also this like co-standard basis, and it is defined by bar involution, or like Gorsky-Negut call it declarative bond involution. So it's an involution which sends Q to Q inverse. E and F are just E and F. I mean, by E and F, I mean Chevrolet generators of quantum affine, and Ki becomes Ki inverse. Okay, that's the involution, and I claim that this involution actually descends to Fock module and to this Fi. Sorry, I call maybe sometimes I'm calling this integrable level 1 representation. Sometimes I'm calling this Fock module. Sorry about this. Okay, so it descends to this Fi, and so you can just take your standard basis and apply this involution, and that's it. This is your co-standard basis. Okay, and as I mentioned before, K-theory of Hilbert scheme is actually your Fock module for quantum toroidal, and as a vector space, it's the same as twisted Fock module. So so let me state our conjecture with like an update of Gorsky-Negut's conjecture. Our conjecture states, first of all, that Gorsky-Negut's conjecture is true, and then that action. So what do we have? We have action of quantum affine algebra on K-theory. How did it happen? Like, as I said, K-theory is the same as Fock space, is the same vector space as twisted Fock space. That's it. And I claim that on the last slide, we actually identified twisted Fock space, this Fi, with this representation of quantum affine algebra. But so what we did, we like did it in an opposite way, maybe. So we started with this Fi, and we defined an action of quantum toroidal on it. And this action is basically twisted Fock module. So when we know it, we identify these spaces. So we have like chain of identifications. K-theory equals twisted Fock module, and twisted Fock module equals Fi, representation of quantum affine algebra. And so our conjecture is that this identification maps this this stable envelopes to standard and co-standard bases of Fi respectively. Okay, that's like it's not the end of my talk, but it's like a good point, I guess, to have some questions if there are any. Like, okay. If there are no questions, and if nobody is like lost with all these Fock identifications, let me say just few words about what we are technically doing, like on the bottom. So as I said, this phi, actually these slides are a bit sloppy. I'm really sorry about this. So as I said, this phi I are like deformations of fermions. And in which sense are they deformations? Like fermions were anti-commuting. And now, instead of anti-commuting, they are exchanged by using R matrix. So here's R matrix for quantum affine algebra, and when you want to change phi, I'm using like matrix notation. So what is phi 1z? It's like operators tensor two-dimensional vector space. And what is phi 1z, phi 2z? 1 and 2 means that like there are two-dimensional vector spaces, and this is element of it's like an operator tensor C2 tensor C2, like here was Cn here, and now I'm considering case n equals 2. That's why I have C2 here. Okay, and when these are deformed fermions, and when I interchange them, then R matrix appears. And this is very natural, since R matrix is an intertwiner interchanging evaluation representations. Okay, and this formula, like the first row of this formula was known before, like it's in Jimbo Miva book, but Jimbo Miva, I'm not really sure. Maybe they consider this Z and W to be like numbers, not formal variables. And therefore, in the book, this delta function is actually missing. So if anybody knows a reference where like you've got these relations that when you interchange vertex operators, then they appear R matrix and also some funny delta function. If you know a reference, please tell us, we will be very interested. Okay, so it's also this like similar story for this dual vertex operators. So these were like C2, this was like here appear dual C2, but his R inverse, his R, but that's like technical points. Also, there are like some different normalizations of R matrix. Here I put just R, here tilde, here R bar. I don't want to bother you with all these normalizations, but okay, that's our contribution from theory of vertex operators of quantum affine algebras. And now, with this in mind, we can, okay, I'll give you one very sloppy calculation. I hope I'm not going to with like too many details. When we are checking like relations for quantum affine algebra, we must check that EZ EW equals EW EZ times some factor, some rational function. And let me be very sloppy and not concerned with this rational function multiple. So we are starting EZ EW. We just put our formula, then we exchange F, phi, Z, and psi. We just exchange them, and actually they just appear a rational multiple when we do this. And we are in this stage. So here are just C2 star tensor C2 star with coefficients in operators. Here is C2 tensor C2. So we like have vectors and covectors, and we take a natural pairing of them with some operator in the middle. Then we apply our key property. So we interchange this phi, and here our matrix appears, and we interchange are inverse, to be honest. And we interchange this psi, and here our matrix appears. Now we have to, so there were like delta functions, but these delta functions actually cancel, they are annihilated by this rational multiple. So but they will be important if we commute like easy with FW. Then they will play their role, and without them, all this will be wrong. Okay. Okay, let us forget about these delta functions. And so now we have like two R matrices. And I claim that this is like a key property, that R matrix commute with this EZ tensor EW. So this R matrix actually cancels. And that's it. We like change the places, and what we still need to do, like to interchange this phi and psi, and as I told you, this is just rational multiple, and that's it. We interchanged EZ and EW. Okay, so maybe I finished in 1 hour instead 90 minutes, but maybe not really finished, but I won't be talking to 90 minutes surely, but maybe it's not bad at all. Okay, so what are like further developments and open questions for me? So what I really want to do is to find a matrix element for this phi and psi in McDonald basis. So as I told you, we've got a representation of quantum affine algebra, and now there's action of this quantum toroidal GL1, and since there are McDonald operators, and eigenvectors of these McDonald operators are their eigenvectors, I call it McDonald basis. And it's very interesting to study matrix coefficients of these operators, to learn whether they have some factorized form. And actually, Andrei told me some very interesting conjectures what these operators could be. But as far as I understand, the only way to compare it with some known operators is to calculate them in McDonald basis. So yes, this leads me to the second question: what are these phi and psi geometrically? And also, I would be happy to see QKZ. Actually, QKZ comes as matrix solution of QKZ comes like a matrix coefficients of these vertex operators for quantum affine algebras. And another story which I want to study is about finitization. So we can like take tensor product of evaluation representation of quantum affine algebra. As I told you, or maybe not exactly told you, but it's like known that there's like Schur-Weil duality. And what is centralizer of this UQ Gillen head? The centralizer is affine Hecke algebra. And actually, I claim that affine Hecke algebra, the action of this action of affine Hecke algebra is quite classical on this space, and I claim that this action can be extended to double affine Hecke algebra. Actually, it's not hard. to obtain whole double affine Hecke algebra, you just need this pi operator, exterior automorphism, and this pi operator actually takes the last multiple, it puts it on the first place, and act by some very particular metrics on the first multiple. So we've got like, so what I basically said is that we have action of double affine Hecke algebra, and it's classical that quantum toroidal algebra maps. Oh, sorry, I put surjection arrow here, it's wrong. Actually, the image is spherical double affine Hecke algebra, and I think that this is very nice, and this representation is actually like twisted representation of twisted polynomial representation. So Cherednik algebra has very standard polynomial representation, and you can also twist it by an element of SL2Z. Yes, and I think that this is finite dimensional representation, and therefore many very explicit things can be computed here. Okay, I guess that's it. Thank you very much for your attention. Sorry for being like too early. Are there any questions? Are everybody dead?
All right, time for questions.
I have a vague question. So there's this elliptic stable basis, and that comes with some parameter, and if I specialize it in certain ways, I get the K-theoretic stable basis. So this should somehow interpolate between all these different stable bases. Is there, does that have some kind of implications for this algebra action, or is there some way to see that you get these standards and co-standards from this elliptic stable basis, or is this elliptic picture somehow lurking behind these algebras you construct?
Well, this is unknown, I guess. So like I tried to communicate with Andrei Smirnov and Yasha Kononov about this, but we do not see connection yet. Yes, probably Yasha Kononov and Andrei Smirnov is another group who are challenging the conjecture, and maybe we will have like 3 proofs, hopefully. Yes, but I would be really happy to see connection of my work and their work, but I don't know yet. And what is nice that I do have this standard basis in my picture, and as far as I understand, they don't really have standard basis, but maybe I'm wrong.
Maybe we should, yeah, actually be good to hear from Andrei and Yasha on this or other topic later in the run of the seminar.
I would be very happy.
More questions? All right, speaking of hearing from Andrei and Yasha later in the seminar, an announcement. I just heard the confirmation. So next week we have Noah, and then Rozansky is confirming that he's going to give a mini course after that. And then it's not clear how many lectures there are going to be, but when they conclude, there'll be Sam, and then we'll see. So that's the plan. So it's Noah, and then some unspecified lectures, some unspecified number of lectures by Rozansky. So that's the plan for the seminar for now. All right, thanks, Roma. That was a great talk. Thank you so much. And
thank you.
And, I guess also thanks to Gus for giving a different talk earlier in the day. So, all right, thanks everybody. We'll see you next week.
See you.